Let's talk about verifying solutions to differential equations and solving initial value problems. First, what's an initial value problem? Let's find a solution to the differential equation dy dx equals x squared. Okay, the derivative of a function is x squared. We know what the solution is. The function is y equals x cubed over 3 plus c. That's the general solution. Now suppose I add with initial condition y of 3 equals 5. This is the general solution to this differential equation. Now that we throw in this condition, we can figure out what c is because there's only one value of c that's going to work. So if y of 3 equals 5, here's our function for y. That means y is 5 when x equals 3. So basically we plug in x equals 3, y equals 5. Do that and you get 5 equals 3 cubed over 3 plus c. In other words, 27 thirds plus c, which is 9 plus c. So 5 equals 9 plus c. That means c equals negative 4. And our solution is no longer y equals x cubed over 3 plus c. Now that we have the initial condition, we can say that the solution is y equals x cubed over 3 minus 4. So the initial condition enabled us to nail down what c actually is. This is an example of initial value problem because you're given a differential equation and you're told the initial value or an initial value of the function y. Let's talk about verifying solutions to differential equations. Determine if the function y equals sine x is a solution to the differential equation d squared y dx squared equals y. So again, our solution or our proposed solution is y equals sine x. Let's see if it fits the differential equation. The left side is d squared y dx squared. In other words, the second derivative of y. Gosh, what is that? Well, if y equals sine x, the first derivative of y is cosine x. And so the second derivative of y, d squared y dx squared, in other words, y double prime, that's going to be negative sine x. Okay, so the left side of this differential equation is negative sine x. Now let's consider the right side. The right side is y. And in this case, y equals sine x. Okay, now check this out. The left side is negative sine x, and the right side is sine x. Oh, those two aren't equal to each other. Close, but yeah, not close enough. So the function y equals sine x is not a solution to the differential equation. Verify that the function y equals c e to the x is a solution to the differential equation dy dx equals y. Let's do it. So we have y equals c to the x. That's supposedly our solution. The left side, dy dx, is going to be the derivative of y. Well, the derivative c e to the x, that's just going to be c e to the x. C is a constant, and e to the x is its own derivative. So the left side is simply c e to the x. The right side of the differential equation, that's y. Well, we know what y is. Y equals c e to the x. Hey, check this out. The left side equals the right side, so it works out. Y equals c to the x fits this differential equation. Therefore, y equals c e to the x is a solution to this differential equation. Now let's find a solution to that differential equation dy dx equals y with initial condition y of 0 equals 7. So again, same differential equation, but now we're told that y of 0 equals 7. So we know the solution to the differential equation is of the form y equals c e to the x. Since we're told that y of 0 is 7, that enables us to figure out what c is. Plug in y equals 7, x equals 0, and we get 7 equals c e to the 0. In other words, c, well, that means c is going to be 7. So our solution to the differential equation is no longer just plain y equals c e to the x. We've nailed down what c is. The solution is y equals 7 e to the x. And again, we were able to do that because we were told this additional piece of information, this initial value. Verify that y equals 1 over 1 plus c e to the negative x is a one-parameter family of solutions of the first-order differential equation y prime equals y minus y squared. So when we say one-parameter family, we mean, okay, it's a family of functions and it has a parameter in it, namely c. C can be really any value. Okay, we're going to rewrite y as 1 plus c e to the negative x to the negative 1. We do that because it's easier to take derivatives when we write it that way. So the left side is going to be y prime, and y prime, well, if we regard y in this way, y prime is going to be negative 1 plus c e to the negative x to the negative 2 times the derivative of the stuff that's on the inside. Well, the derivative of this is going to be c e to the x times negative 1, In other words, negative c e to the negative x. So the negative signs cancel, and we're just left with c e to the negative x over 1 plus c e to the negative x squared. Okay, that's the left side. Now let's consider the right side of the differential equation, namely y minus y squared. Okay, here's y, and y squared is just going to look like this. You're just squaring the denominator. So let's find a least common denominator. That's just going to be 1 plus c e to the negative x squared. So for this, multiply top and bottom by 1 plus c e to the negative x, and this is what we end up with. So we have this minus 1 over 1 plus c e to the negative x squared. They have the same denominator, so we can rewrite this as 1 plus c e to the negative x minus 1. In other words, c e to the negative x all over 1 plus c e to the negative x squared. Okay, now check this out. That's what we had on the left side. This is the left side. This is the right side. Those are equal. So if y equals 1 over 1 plus c e to the negative x, we get a solution to this differential equation. So that's the solution. We've verified it. Now let's find a solution of the first order initial value problem, IVP. Y prime equals y minus y squared, y of 0 equals 1/12. Again, same differential equation, so we know what the solution is. The solution to this is going to be y equals 1 over 1 plus c e to the negative x. Let's plug in x equals 0, y equals 12. So when we do that, we end up with 1/12. Again, y equals 1/12. 1/12 equals 1 over 1 plus c e to the 0, because in this case x is 0. In other words, it's 1 over 1 plus c. So if 1/12 equals 1 over 1 plus c, that means c must be 11. So our solution is going to be y equals 1 over 1 plus 11 e to the negative x. The function x equals c1 cosine 2t plus c2 sine 2t is a two-parameter family of solutions of the second order differential equation x double prime plus x equals 0. Find a solution to the initial value problem x double prime plus x equals 0, x of 0 equals 6, x prime of 0 equals 18. Okay, this is a two-parameter family of solutions because you have c1 and c2 as parameters. We know that that's going to be the solution to this differential equation. And so to find a solution to an initial value problem, since there are two parameters, we need two initial conditions. So we're told that x of 0 equals 6 and x prime of 0 is 18. Okay, let's see how we can use those. We know that this is a solution to the differential equation, so let's just plug in x equals 0. Let's just plug in x equals 6 and t equals 0 into this differential equation. When we do that, we get 6 equals c1 cosine 0 plus c2 sine 0. In other words, 6 equals c1 times 1 plus c2 times 0, which is just c1. So in other words, c1 equals 6. Okay, so we've solved for c1. Now let's solve for the other variable, the other parameter, c2. Okay, x prime equals negative 2c, and all I'm doing is taking the derivative of this function. If this is x, we know how to find x prime using the chain rule. The derivative of this is going to be negative 2c1 sine 2t plus 2c2 cosine 2t. In other words, it's going to be 18, again, x prime of 0 is 18, equals negative 2 times 6 sine 0, again, because we know that c1, we found earlier that c1 was 6. So we plug this in, negative 2 times c1, in other words, negative 2 times 6 sine 0 plus 2c2 cosine 0. We're just plugging in t equals 0. Well, sine 0 is 0, so that just drops out. Yeah, so we have negative 6 times 0. Well, that's just 0. Plus 2c2 times 1 equals 2c2. So the right side just simplifies to 2c2 because this drops out. So we have 18 equals 2c2. That means c2 equals 9. And we're done. So we know that c1 is 6 and c2 is 9. So that means the solution to this initial value problem is x equals 6 cosine 2t plus 9 sine 2t.